Okay, testing. Good, we are live. Okay, everybody, welcome to the first live/Zoom edition of the Bureau Friday Seminar Series. I'm the host, Kelly Torrey, and today our speaker is going to be Dr. Michael Young. Dr. Michael Young is a senior research scientist at the Bureau of Economic Geology, Jackson School of Geosciences at UT Austin, of course, which many of you guys know. He earned his PhD in soil and water science, specializing in soil physics and hydrology from the University of Arizona. Before joining the Bureau in 2010, he held academic research positions at the Desert Research Institute in Nevada and the Georgia Institute of Technology. His current research includes water and land impacts from energy development, the connection between water resources, land development, and human interactions, and water conservation at the community level using integrated modeling. Dr. Young has authored or co-authored over 90 peer-reviewed journal articles and given 200 plus presentations at scholarly meetings. He is a fellow of the Geological Society of America and Soil Science Society of America. And today he's going to be presenting his work on regional land impacts in Texas from energy development. And just as a reminder for you guys, please don't ask questions during the talk. Let's hold them till the end, okay? Great, all right. Michael, take it away.
Okay, so am I on mic or am I muted? I'm good? Okay. It's so unusual actually to be talking to in live. So this is sort of like a Zoom meeting, only you have to stand up during it. Oh, geez. So I dropped that joke and nothing happened. Am I on? Okay. You can see I'm not a tech guy. So, okay. So it's great to be here and be here in person and to talk to everybody here and everybody sort of out there in Zoom land. I want to talk a little bit about some of the work that we've been doing upstairs. So even when I was associate director for since 2013, which has been looking kind of at regional scale land impacts from energy development, and we're thinking all kinds of energy from oil and gas, wind and solar. and I thought, hey, it would be a good idea to let people know what's going on. One of the questions at the visiting committee meeting in August was, hey, we have a sense of where oil and gas is likely to be, produced. Do we have the same knowledge with wind and solar? And so with questions like that, I was like, yeah, we do have some sense of it. So that's kind of what I'm going to talk about. And so, okay, let's see if I can do the impossible. Okay, so we typically talk about land impacts in terms of footprints, right? Which some people call surface power density. And this graph here shows essentially, in the gray boxes, this is fossil energy, and in the not gray boxes, this is more or less renewable. And you can, and you get a sense that the power density, which is going to be sort of the power divided by the land footprint, is much, much higher for natural gas than it is, and nuclear and oil than it is for renewables. And we know that. We know that fossil energy has a much higher energy density in terms of, we could look at it in terms of, watts per barrel or watts per acre, those kinds of units. And one of the things that we know that these are happening, and as the country starts thinking about transitioning, and a lot of discussion about transitioning from fossil energy to produce electricity to renewables, one of the things that is now starting to make it into the media a little bit more is the fact that it's going to require a lot more land, and that the energy is going to be produced, the renewable energy is basically being produced away from the load centers where people live. So then you have to transmit the power from where the electrons are produced to where the people live. And so there's a much higher land alteration patterns when you're really talking about the utility scale renewable energy. And so we're trying to kind of manage that here in Texas. We went through Winter Storm Uri, which was really somewhat of a catastrophic impact, in my opinion, that really showed how, I think, fragile both the grid and the connection of the grid to water and food really has become during these kinds of black swan events. And so, okay, so we sort of have a reality check. And the reality check is that we really do need to have, available and affordable access to water, food, land, and energy. So I put Maslow's hierarchy of needs in here. And, if you go down to the bottom, you know, there's air, water, food, shelter, sleep, clothing, and then there's reproduction. We're not going to do the reproduction part here. We're only going to focus on the physical things that the Bureau more or less works on, and that's not in our mission statement. And so, and you know, we know that every solution is going to come at some cost to the environment. There is no energy source that is basically free, and so, but we don't really know if we're talking about transitioning from fossil energy and things of that nature to renewables at the grand scale. I mean, I'm talking about at the national scale. We don't know what the long-term effects are going to be on both land as well as the supply chain, which I'll talk about. So I put the goal down here. What's the likelihood of a particular type of energy source being developed in a particular location over the next several decades? And what's the impact of that happening? So we've developed a workflow. A lot of this work has been started with funding from the Mitchell Foundation, from the JP Morgan Chase Foundation that dates back 8 or 9 years or so. And we've come up with a way of looking at this, and I'll show a flow diagram, somewhat cheesy flow diagram later. But we need to map existing infrastructure, what has been constructed out in the landscape already. We identify areas that are excluded from future development, and these would be areas that are already producing energy. In other words, if there's an oil and gas well somewhere, we're not going to put a solar panel on top of it. Parks, cemeteries, rivers, cities, those are generally excluded from future development. Like Big Bend National Park, for example, we're not going to be putting oil wells out there. And then we try to evaluate the resource potential. And you know, there's a lot of work being done at the Bureau on this, and so we'll talk a little bit about that. And then we start looking at what are the scenarios going forward for the next 30 years. We're really looking kind of at mid-century. We've come up with a numerical scheme to identify probabilities of where particularly renewables are going to be placed on the landscape, and I'll talk about that. And then we overlay the you know, where we think the energy might be located, with where we think the land has the highest value. And the purpose of that is that if we're going to be adding more energy development in a particular area, we want to do it in locations where the land has already been impacted or is of low quality. Like, we don't want to go to a pristine grassland habitat for, you know, an endangered species if there are options for companies to be able to deploy infrastructure elsewhere. And so hopefully, yeah, you can kind of see up on the top, it looks like everything's a little bit blocked there. But so this is what it looks like in the last 10 years of drilling in excellent. So we're going to get IT support. Fabulous. Thank you. These guys are great. Whoop. Awesome. Thank you. And so, so this is the amount of exploration that's occurred in the Permian Basin, really in the last 10 years. Of course, the vast majority of these are unconventional wells in the Midland and Delaware basins. And the red outline is sort of one of many renditions of the extent of the Delaware. And one of the things, so this heavy line, which you're going to be seeing a lot of, that kind of hits what we would call the southern three counties, the tri-county area, is part of the field site that we use for a Mitchell Foundation funded project called Respect Big Bend, that was really seeking to get a much better handle on the land quality and the land value in the tri-county area, and then communicating that to landowners, those that live in, you know, in Alpine and Presidio and, you know, the other communities out there, so that they have a better understanding of what they have on their properties, and then that helps them to make better decisions when they're negotiating with energy companies. And so you're going to see this kind of southern three county area quite a bit. And so, you know, for those, whoops, let's see. There it goes. All right. So I did part of this talk at the Energy Institute earlier this year. And one of the questions was, well, you know, there is a fair amount of energy development that's occurring outside of the Delaware. And so we've also plotted up all the wells that have been drilled This is every well that's in the database outside of the Permian Basin. And of particular notice is down here in Southwest Presidio County, where there has been some exploration, but there's not likely to be the kind of intensive activity that we have seen in the Delaware Basin and in the area around Midland Basin and elsewhere. But this just kind of shows, yeah, there is some energy development outside, but to the relief, I suppose, of some of the folks in RBB, it's not likely to be a really large scale exploration area. And so we then said, all right, we know where the wells are located. We can estimate what the size of the drill pad is. We estimated that more or less at about 15,000 square meters. It's somewhere between 3 and 5 acres per well pad. And that is what we are calling land alteration. We're less concerned about the number of wells. We're more concerned about the expression of the well on the landscape. And so then we will get into, well, what is the number of wells per pad? Is it 3? Is it 10? Is it 1? How does that change what we can expect for land alteration? And so the graph on the left here shows the direct alteration in terms of percent of square kilometer. And so the darker areas, of course, they're higher. These numbers here between about 30 and 50% of the land has been directly altered. This would be roads, pipelines, and drill pads primarily. And of course, and compressor stations and things like that. So you see it's a fairly light color with a couple of other areas. On the right is indirect alteration, which from an ecosystem standpoint is about a buffer of about 100 meters outside of the direct alteration. So, and so the ecologists and the biologists have been looking at this for quite a while. And when they look at things like migration pathways of animals and things like that, there is some buffer area between the land that's been directly disturbed and the land that is truly undisturbed. And that buffer is about 100 meters. But when you add that around the drill pads, it increases quite a bit what the percent of the land alteration is. Okay, so now we have some sense of what's happened in the past. Now let's think about going forward. And so we came up with a relatively straightforward approach of looking at saying, if the land has been producing oil and gas over the last 10 years, we assume that that's unconventional development, and we assume, therefore, that there's going to be some development going forward in the future. And so we looked at the slope of the oil, not only the oil production per square kilometer, but also the number of pads that have been constructed per square kilometer. And so we then came up with this, this very simple differential equation. We used the chain rule to identify the number of pads that have changed over time. And if that number is positive, and basically non-negative or non-zero, then we assume there's going to be some trend going forward into the future. Now, this is somewhat inexact, and it was done before the Tora Consortium has come up with a much better sort of geologic estimate of what really is expected to be drilled in the Wolfcamp A and B and Bone Springs and other units that are out there that we have a much better knowledge on. But this was just kind of one estimate, and there's lots of different ways of doing it, and it does give us a sense of where things are going to be occurring. For example, the dark, kind of brown colors that are in here are areas where there has been positive development over the last 10 years or so, and therefore we expect that to occur again in the future. And this is just a picture from Chen Yang's paper in SPE last year that was really looking at where were the wells actually drilled. And after 2017, you can see all these red, very small lines that indicate the actual laterals and the lateral directions. This is where this is the wells that have been drilled, and then this is the EUR of the wells that are expected in the future. So there's some correspondence between what we came up with here and what Chen and the Tora Consortium has come up with in the future. So we felt reasonably confident that we have a sense of this. And so we then came up with different scenarios because the landowners are in some cases asking energy companies, hey, do some conservation work out here on my property. And one way to do that would be to increase the number of wells per pad. So we assumed our business as usual case is going to be 3 wells per pad. And we were informed of this by multiple companies that that's kind of a reasonably rough number, and that a high conservation scenario, in other words, energy development with low impact, would be more wells per pad. Okay, so that's our high conservation scenario is 9 wells per pad, and our low conservation scenario, our high alteration, would be 1 well per pad. So that just kind of gives you a sense, and we're calling the BAU the medium scenario. And we've done the same thing for renewables so that we can match everything up side by side. But you can see going forward up to 2050 that there are some areas where, you know, we're really looking at essentially the entire square kilometer is going to be altered, and it goes all the way up into Culberson County, right into New Mexico. We have done this for the entire Permian Basin, but this is just our study area, which we did for the Mitchell Foundation. And that's about, to give you a rough estimate, it's about 113,000 square kilometers. So it's about the size of Ohio, I think. And so this is the medium, and then this is the high impact scenario. Again, 1 well per pad going forward. And you can see that there's quite a bit more when you consider the wells that'll be drilled. I think we assumed 250,000 wells over the next 30 years. And so anyway, that's about the number. And so, okay, so that's what we kind of expect for fossil energy development. And now we're going to talk a little bit about solar and wind. So this morning, in a low-grade panic, I went on to the ERCOT page and was able to download and get an updated estimate of how much wind and solar is expected to be constructed in West Texas between now and 2025. These graphs are updated and publicly available by ERCOT every month. And so what it's showing here, and so on the left is the capacity for solar, and it's in megawatts. So right now in Texas, we have approximately, I don't know, we can run the numbers, just under 9 gigawatts of solar capacity in the state of Texas. By the end of the year, the expectation is we're going to be just over 10 gigawatts of capacity. And I put the word capacity in quotes because what's the capacity and the production are very different things. And so we are going to be thinking about the production of electrons much more than the capacity, although the capacity becomes important. And this is sort of what's expected. And so the maroon color here, this is, you know, A&M's colors. This is actually what has been, the interconnection agreement have been filed with ERCOT, and they have posted their finances. So these are much more likely projects to be constructed in reality than, say, these green ones where a company has submitted the interconnection agreement, but they have no money. So, okay, is that going to happen? Who knows? In the end, we're really looking potentially, if all of these become reality, we're looking at 30 gigawatts of solar capacity between now and 2025. And again, these are updated all the time, and I'm sure that companies are coming into a very fluid and dynamic situation each time. This is what wind is. So by the end of this year, we expect 34 gigawatts of wind capacity. This is across the entire state. And there will be some nominal increase going forward. You can see the maroon here. By 2022, there's an additional 4.5 gigawatts of capacity. But for the most part, it's really starting to kind of taper off. And you can see that we got 39 gigawatts at the end of 2023. And at the end of 2023, it'd be 29 gigawatts for solar if everything is added the way they're expecting. So there's going to be a correspondence between the two. And of course, wind and solar have different impacts on landscapes, right? Because solar is on the ground, constructed. It's usually, the land is usually bladed and graded. The solar panels are put on the ground and then it's fenced off. Wind is totally different. You have a single tower, and then you have the blades that are 90 meters in length. And you know how we conceptualize what the impact is for wind has a huge impact on what the land alteration is. And you know, I'll talk about that in just a second. So I want to bring up batteries because we know the intermittency of renewables is a huge issue. Europe is dealing with this right now because apparently the wind is not blowing in Europe, and so they have had much less production from their wind energy, which is causing a ripple effect throughout their grid. And so this is So this looks like a big number. You know, that we're looking at about 5 gigawatts of storage that's expected by 2023. But when you scale everything based on the y-axis, the numbers are so small you can't even read them. So from the standpoint of energy storage, Texas has a long way to go in order to capture the electrons that are being generated from the renewables into, you know, something that would address intermittency. And so as part of the RBB project, we contracted with folks that are in Mike Weber's group, and they ran a model. So this is Josh Rhodes and Tom Deachin, who ran a capacity expansion model that ERCOT would typically use, and asking the question, what do we expect you know, the entire grid mix to look like across the state of Texas in 30 years from now? It's a basic question. Of course, you know, we can look in the crystal ball. Everybody's going to have a different crystal ball. We don't know for sure. But they went ahead and looked at a wide variety of assumptions in terms of what do we expect the demand to be, what do we expect gas prices, natural gas prices to be, since that's what's sort of driving a lot of the renewables, and you know, all kinds of different factors. And they came up with different numbers for all of the regions of Texas. You can't just look at one of these regions and say this is what it's going to be, because the grid is interconnected across the state, and the electrons are moving around freely between these sectors. So we only focused on ERCOT Region 2, which is slightly larger than our field site. You can remember our field site was basically all the way here. It goes to Val Verde County. It ends in Culberson. And so we scaled everything based on that, because we are actually not getting a higher fidelity of the data. We're only getting it per region. And so this is what the breakdown would look like for the entire state. So the yellow bars are solar and the blue bars are wind. And I'll actually get those numbers on there. And it makes sense, right? Because the further you go west to Texas, the sunnier it gets. And because the humidity is lower, the global horizontal irradiance of the sun's power is higher the further west you go. So the model, not really knowing issues of like, you know, of grid stability and transmission capacity, it's more or less moving things closer to the west than it is in our region. And we know that the wind power density is much higher in the east of our region. And so the wind is more likely to be along that corridor to the eastern part of our site, all the way down to Val Verde County. And then, so this is the BAU case, and then this is the high development scenario. And you can see the bars are a little larger, but they're not really all that much larger. And eventually it starts to top out in West Texas. And a lot of that is actually governed by congestion on the ERCOT power lines. And so we then went through and said, well, look, we know we're going to get 6 or 7 or 10 gigawatts of new solar. Let's go ahead and distribute that across our county so we can get a better sense of where these things might be located. And that's what you're looking at here. So there's new solar at 10.5 gigawatts. The size of the, this is the current capacity. You see little yellow bubbles, and then you see a bunch of blue bubbles for wind. And so looking at the bottom row here, this is what we expect for solar to be, and in these various counties. Of course, a lot of this is going to depend on the company's ability to move electrons. And so we've come up with a kind of a numerical approach to estimating that. And so, you know, a correspondence to oil and gas, what's the EUR, what's the technical recoverable resource in wind and energy space, is the global horizontal irradiance, which is on the left, and the darker colors are more sunny. And then the wind energy development is basically, and what we are calling basically wind power density. That's what's here on the right. And you can see that the higher, the hot colors basically indicate higher wind, and therefore more likely to spin the turbines. And these little symbols here are where the turbines exist right now. And they are certainly following this, power density map. And so our question then is, all right, we have a sense of how much we can expect in the future. Now, where is it going to be located? And this gets really tricky because we're dealing with such a large area, and the footprint for wind and solar is relatively small. So it could go, we're talking about hundreds of thousands of possible choices of where the wind and the solar are going to be located. So we talked with wind and solar companies and said, hey, when y'all get into that dark and smoky room and you say, we want to put it here, what do you consider as a criteria for where you put it? And so on the right-hand side, these are the factors that the companies have told us about. They said, look, if it's not sunny, we don't want to go there. If there's no power line, we don't want to go there. So what's the proximity to a CREZ line, for example? What's the proximity to roads? Because if there's no roads, then we have to cut the roads that builds into their CapEx costs. And then very importantly, what is the proximity to existing infrastructure? If the solar and the wind aren't sitting on top of one another, that means that the facility that's closest to the power lines has the easiest time getting their electrons to market. And if you happen to be on the wrong side of that, then you're almost certainly going to get hit with line congestion. So that means that the value of your electrons is less. That means the banks have less likelihood of getting their money back. And so the entire projects can fall apart if there's too much congestion on the line. So this is probably going to be the choke point going forward. So these are our parameters, right, that we considered. There could be lots of others, but that's what we used. And then we weighted them based on the importance that the companies felt they were important. And it was amazing, actually, how different they viewed it. Some people said, we don't care what the GHI is, the horizontal irradiance, the sunlight, because it's sunny all over Texas and we'll make it work. Some companies said, if there's no power line nearby, won't even consider it. Other companies said, we'll install our own power line, so we don't care about that. So the numbers were everywhere. And so we were like, my God, there's no commonality in terms of how they're viewing these parameters. So we came up with a weighting scheme that would allow us to investigate where the facilities would be located, depending on, a variety of different weights, an entire rubric of weights. And here's the equation. We got the sum. There's the parameter times the weight. The weight's all equal to 1. And then we run the model thousands of times, and we see how many of these areas are chosen by this Monte Carlo simulation. And we're now running it 3,000 times and not 2,500. So we have 30 combinations of weights, and we run it 3,000 times, so it's 90,000 simulations. And so it's definitely a lot of computational load. And so if we mix the weights, we focus mostly on weight 1, so that's the resource potential at 60%. Then this is basically what the probability is of a facility being chosen. And on the right, you can see this stippled pattern. These are the actual cells that were chosen by the algorithm. And the maximum number of times that a cell was chosen randomly was only 1.8%. So this is almost a completely uniform distribution of where the facilities could be located. And, and so that doesn't really help us that much because it could be anywhere. But if we change the weights, and we assume that the power lines are the things that matter the most, then the facilities are picked much more consistently, or the land is picked much more consistently closer to the transmission lines. And so here, the maximum occurrence is 96.4% as you get closer to the power lines. And you can see these are the actual power lines that are out there right now. And these are all publicly available data sets. So these are what the results are. We're assuming that the medium area is of land for any solar facility is going to be 2.6 square kilometers. That's just over 1,000 acres, or 700 acres, I think. And then on the left these are the different capacities that we're sort of expecting, the number of facilities, the total area that's going to be needed, and then the acreage. We've been presenting this to the media and others, and so they would like to have things in square kilometers. It's a bit difficult for them, but it's 247 acres per square kilometer, in case you're wondering. And then these are where the profiles are. And this one graph here is what led us down this rabbit hole of Monte Carlo modeling, because the black dots here is what one iteration looks like. And when we presented this to the stakeholders, they're like, hey, that's my land. What do you mean there's going to be a facility on my land? So we didn't want people to go nonlinear on us. And we said, look, these are just probabilities. That's really hard for people to conceptualize when it's on a facility's on top of somebody's house. So we then ran through and said, we're only going to calculate probabilities and present probability rasters instead of actual locations, which I think is much more appropriate given what we're trying to do. And then this is the wind development, same deal. This is the capacity projected, low, medium, high, the number of facilities. The area is much, much larger than solar. So 2.6 to 47 square kilometers. Now, why is that? And the reason is that we are assuming that the land impact is more than just the tower itself and the footing around the tower, even though the land may still be in productivity in some way. We're assuming it's the diameter of the blades of the turbine and the white space in between the turbines for a concentrated number of turbines in an area. So if you go out to the field, you say we're going to install 10 of these 3 megawatt turbines, we are simply circumscribing all of the area inside that support area as being altered, quote unquote. A lot of people are doing it in different ways. This is just the way that we did it, and we caveat that accordingly. And you can see the area when you get into the high impact, it's a big number. It's 2.7 million acres, right? So it's a large number. And if we add everything up, and we say, okay, we're going to add up all wind and solar, oil and gas. This is the range of possible future direct land use, anywhere between 3,500, 3,600 to 17,000 square kilometers. So it's basically all in. And so the question now is, if we know how much is going to be land is going to be needed, do we know what the effect is going to be on the land itself? So working with the Nature Conservancy on the RBB team, we came up with a list of attributes that basically kind of describe the land. Everything from intact systems to grasslands, riparian and wetlands and springs and mule deer. I mean, there's all kinds of things that the Nature Conservancy does as part of their mission, is to account and sort of asset map lots of these different features that are on the landscape. And so we created these land attribute maps and then scaled them that says this is the highest value and this is the lowest value. So we know where the high value landscapes are. And when we look at this, you can see here's our RBB area. And so the blue colors are the areas where we have higher acreage of these sort of favorable attributes. And so down here, so the bluer it is, the more of those attributes that exist. And the dark areas, dark brown, there's fewer attributes. And again, there's the list: view sheds, nighttime lights, open spaces, springs and riparian areas, and so on. And so then we then color code everything, and we show the areas where the values are higher and where the values are lower. These were done with equal weights all the way through. They were all normalized, summed together, and then plotted up accordingly. The way that we did it, we actually added variable weights to it. So it's a slightly different approach. But you can see the green areas, much higher value, and the purple areas over in the Midland Odessa area is lower value. And that, again, is not a judgment. It's more of, okay, this is what the land currently has. So now we know how much energy is going to be produced. We have a sense of where, and now we know where the land is higher value. And so we sort of take this Venn diagram approach and we look at sort of the different impacts of wind and solar. And these are the kinds of things that wind can impact. Bird and bat kills, there's sound pollution, there's light pollution, there's habitat degradation, and solar changes the albedo, which is the amount of incoming solar radiation that's absorbed by the land, and how much is reflected back. So it changes the reflectivity of the landscape. It alters the surface hydrology. There's a variety of things here. And then in the center is where you put energy out there, you're going to be affecting land use and land cover and things like that. And so Catherine Jones, who's my master's student, who's one of the very few people in the audience who came down here, basically ran an example of if we have a wind facility that's constructed, what effect might this have on a particular type of an owl? And so here, the potential impact of wind turbines, you can see we're still using the RBB area, but we're not focused on the Tri-County. We're focused much more on Pecos, Upton, and Crockett County, where the wind turbines are located. And then Catherine chose the western burrowing owl as the species of concern. And this is now a global species of concern. It's endangered in Canada and in Mexico, and it is just sort of on the concerned list here in the US. And we're using a platform that's called the Natural Capital, Stanford's Natural Capital platform, that basically looks at ecosystem services and ecosystem impacts from land use change. And so there's an entire workflow that is set up where you take these land attribute rasters, you import that into their model, and then when you start to alter the land, it has an impact on what the quality of the land is. And then from that, you can then begin to calculate, if you choose to, what is the dollar value, the ecosystem service value from an economic standpoint, what is the cost of making the land use change. So if the landowner says, I'm gonna make some money by doing energy development on my land, but it's gonna cost me some dollars because there's now an impact on the ecosystem services, that is something that can play into the decision-making and the balance of the landowner. And so this is just an example model output from those 3 counties. Over here is where the wind turbines are. And so there's no degradation in the gray, but the redder you get, the higher the degradation becomes. So if you have areas in here that are very high quality landscape and you start doing land alteration with wind, you can see right away where the conflict is going to be. And so I kind of developed this cheesy flowchart last night, you know, that on what is it we're really doing. We do the energy resources and land resources, and then we intersect the two and we say, hey, is there a conflict? And if the answer is no, then go for it. And if the answer is yes, there is, but does it matter? No, it doesn't matter. In other words, there's an intersection, but it's very, very low impact. Then the answer is no, then you go for it. If the answer is yes, we want to quantify the impacts and start asking, are there things we can do about this? Can we change the location of the facility so that the impact is lower? And if the answer is no, then the landowner and the energy company and society just has to ask the adult question, am I willing to accept the trade-off? Because, hey, you're going to put it out there, but you're going to have a big impact on this land. And okay, now at least you know you're going to be making an informed decision. And if the answer is, yeah, would revising things help? The answers are yes, and okay, then you could then reconsider the location or reconsider the production of energy. I mean, it's fairly straightforward. And this is just kind of how I conceptualize this. And of course, communicating with stakeholders is probably the most important thing. So I put a little bracket underneath all of that. And so this is my animation showing this project that we have just been approved that I'll talk very briefly about. That's called Comparing Electricity Options, or CEO. This is a new IA at the Bureau that was approved by the Vice President's office last Monday, so it's super new. And we have a postdoc, Ata Raymond, who is also one of the few brave souls in the room, and we are trying to come up with a logo. And so this is just his rendition of a logo, and I've offered a free pizza to the students, whoever comes up with the winning logo. So this is my attempt at bribery. And so what are we going to do with this project? We're going to run a life cycle assessment, which is a very broad and comprehensive environmental impact assessment of any kind of supply chain, land use change, anything like that. You can kind of look at this, and a life cycle assessment has it's actually an ISO standardized process. There's models. It's an entire cottage industry, and what we want to do is we want to compare the LCAs for 5 different scenarios. One being combined cycle. Our test case, our kind of base case, is a 500 megawatt combined cycle facility that's producing and so if you run the numbers and you run it for a whole year with a 70% capacity factor, you generate 3 terawatt hours of electricity per year. So it's 500 times 7860 or 8760 times 0.7 gives you 3. And 3 terawatts. So we're gonna use that as our base case, and then say, what is the size of the solar facility needed to match 3 terawatt hours of electricity per year? It's certainly larger than a 500 megawatt capacity. It's probably more than twice that. But that's kind of how we're approaching it. And then we say, what is all the material that's going to be needed to build this facility? And this is all sorts of different materials. And there's the list. And there are the energy options that you see here. Here are the critical materials that are going to be needed: iron, molybdenum, aluminum, cobalt, copper, and lithium, and all of these things that are needed to do this. And of course, this is now we're talking a global supply chain. So this really becomes a much broader type of a thing. And these are the critical materials we're going to be looking at: lithium, cobalt, copper, nickel, and rare earths. And we're going to really do the best that we can to identify the supply chain, where they're being produced, where they're being shipped, how they're being processed, and then how they're being incorporated into particular energy systems. And this is sort of our approach. Phase 1 is just this comparison of a plant-by-plant comparison. Phase 2, which is down here in the purple, is to optimize the energy mix. In other words, we account for intermittency and we ask ourselves, what is the percent of each of these energy sources that would give us the highest continuity and stability of the grid while reducing the environmental impacts to the greatest amount. So this is going to be an optimization. And then finally, we're going to look at what is the cost to the consumer. If we pay 13 cents a kilowatt hour here in the States, and right now I think in Germany it's 35 cents, 36 cents a kilowatt hour in Germany. It's high. It's 3 times what it is here. That's going to have an impact on consumers. It's going to have an impact on the consumers who can least afford to pay it. So what is the overall benefit? How do you balance these benefits here? And that's kind of what the project is. So we have been able, we got a team of students, great students that are all going to be looking at a specific mineral. So we were talking about, lithium, cobalt, copper, and so on. And these are the students that are all working on it. And then each one will also look at the life cycle of a particular energy technology: solar, solar plus batteries, wind, wind plus batteries, and so on. And so Tristan Childress, Gurjan, Ata Rahman, Dave Chapman, and myself are all sort of involved in this. And we have now, at the Bureau, we have economic geology that's been restarted, fabulous. We have mining engineering. We have environmental geosciences and energy economics. So we think we have a pretty good team of people. And we've really been able to get some, we're starting to get some pretty good traction on both the progress as well as just communicating. And of course, we have that logo down there. So, okay, so what are the take-home messages? I can read them, but you can read. And we have to deal with this over the next 30 years. That there's now a societal demand for decarbonizing our energy systems, and that is a train that has left the station. So how are we going to do it, and how are we going to do it so that we can make smart choices without necessarily having a lot of unanticipated, unexpected consequences? So with that, I'm going to stop. And the Mitchell Foundation really inspired a lot of this. Texas Star paid for some of this, the Jackson School, and now CEO IA. And that little bitty font down there says TBD. So in case anybody is squinting, we don't have the members nailed down yet. We just got approval, and we hope the webpage is up in a week. And I'll just stop there, and hopefully there's time for questions. Thanks.
Okay, great. Yeah, Michael, if you want, we'll take the local questions first. And because people don't have a mic, I'm just going to repeat the question that they ask so that people on Zoom can hear.
Yeah.
I have 2 questions. The first one is a real quickie because it lies outside of your scope of work. But is anybody doing a values assessment of building the wall through Big Bend Park?
Okay, the question is anybody doing a values assessment of the impact of building the wall through Big Bend Park?
I'm sure there are people that are doing that. I don't know who they are. I imagine there's different advocacy groups that are working on this very quickly, but I'm just not aware of that.
Well, I realize that was off the scope, but the real question I have is when you were showing the plateauing of wind energy, and then you were talking about the various areas that seem to rely more on proximity to the power lines and things like that. is there any geomorphology in there in terms of limiting wind? Because I flew over it yesterday coming back from Tucson, and you could see how those things are aligned with ridge lines and so on and so forth. So did you all work geomorphology?
So we did. So the question from Chalk is, how did we account for geomorphology? So we're using the wind power density maps from NREL, and we are assuming that that anything greater than, I think it was a 5% slope, is too steep to install these. So we included certain criteria that would exclude certain areas, and geomorphology is a key part of that. And we did the same thing for solar. So if you have, for example, a steep slope, anything greater than, I think it was 5%, and facing, east-facing slope, I mean, those are things that are basically excluded from what we're trying to put on. And so, and these are criteria that were developed by Grace Wu at Los Alamos, or rather Lawrence Berkeley Labs. And we're just using her exclusion criteria to remove certain areas from consideration. Other questions? Rich, I know you have a question. You're out there. I'll just call on you if I don't hear from you. Yeah, Tristan.
So for the land area surrounding the windmills that is included in this impacted area, in what realistic percentage can you bring that impacted area down, or maybe can you realize usage of that so that that number isn't so scary compared to solar?
Yeah, well, I mean, you could just redraw the box. Yeah. And the land, very often, if you drive around, the Panhandle, you can see the land is still in production.
I guess maybe what I'm thinking is comparison of land that is no longer usable versus wind versus solar. Yeah, so here's the thing is, of course, if you are a ground crawling creature, you're a cow, you're fine. But if you're a bird, you're not fine. So how do you think about, your frame of reference is what's happening on the ground. And our frame of reference was simply a little bit larger and including bats and birds. We could change that frame of reference, and many papers do. They say, hey, this is just the roads and the tower footprint. That's it. And but we wanted to think a little bit more broadly. The approach we use is not unique to us. A lot of other people are including that. The turbines and the interaction between the turbines. And so, we just wanted to have full disclosure on that. And it scared a number of people. They're like, wow, that's a big number. And it is a big number. And so, especially in acres. So the challenge then is, okay, for solar, how can you keep the land in production for solar? And there may be some ways to do that. So those footprints could be reduced if we kind of redrew the box and we kind of thought a little bit more broadly about it. Jay.
There's some questions in your chat.
Oh,
yeah. So
I don't know how to do that.
If we don't have any more questions here locally, then yeah, we'll pull up the chat. Just hit escape, please.
Oh.
Yep, and then just hit chat right there, and you've got quite a few questions. Right. So if you want to read them all,
I'll read them.
Okay.
So there's Dina. Thank you. In the list of parameters, how about private versus public land access? We did not include that, Tody. That is in Texas. It's not really a consideration because there's so much private land. But absolutely, this is something to consider. And in fact, if you look at a land alteration map between New Mexico and Texas, especially on the eastern border of New Mexico, the north-south trending boundary, you'll see just really almost a knife edge difference in land quality going from Utah, or rather going from New Mexico to Texas. And we proposed to do a study on what 100 years of land conservation on federal land means in terms of the difference of land quality, but we proposed that to NRCS, but they didn't bite. Anyway, we didn't consider that. Do we factor in? So Peter Ikubel, did you factor in that Western locations are more valuable for solar because they produce solar power later in the day during peak evening electricity demand? And the short answer is yes, we did account for the fact that the further west you go, the later in the day, the sun is still shining. So the model took into account exactly that issue as opposed to a solar field that is constructed in East Texas. So yes, and ERCOT also considers that too, Peter. On the battery end, are considering green as a potential alternative. So Lorena asked about hydrogen. We did not, but we could, and we probably should. For the CEO project, we're just focusing on batteries right now so we can get traction on the project. And if we can expand to other electricity sources and storage options, then we will. But we don't want to get too far ahead of our skis because we'll just end up crashing and burning. And Dave says, great talk, thank you. On any thoughts on what the chances are that local wind and solar power generation on homes could be used? And absolutely, that's known as distributed power. And so one way to reduce the footprint for solar is to put the solar panels on areas that have already been altered, i.e. on homes and buildings and parking, parking lots and things like that. And so that would be a great thing to add. There's a challenge is that every time you put in a new, your home and you're plugging into the grid, it requires the utility companies to actually build hardware to manage your electricity that you're now plugging into the grid. So it turns out to be really difficult for the energy companies, the commercial companies to basically manage that. But I think that's just where innovation comes in and we can do better. Yes, okay, thank you, Alberto. Excellent work since you're including minerals as critical part for sustainability. How critical is storage of electrical energy to make solar and wind reliable? I think it's critical. That's my personal opinion. If we try to match baseload dispatchable power using combined cycle nuclear and others, maybe hydrogen as a way of doing, and even LNG as a way of doing utility scale electricity, and then we backfill all the rest of the electricity demand with renewables, there are ways to basically do that. And I think that in the end, it's going to be a mix of dispatchable baseload and peak renewable with some options, and whatever that percentage is, that is really where we have to get our pencil sharpened and work on that. Yeah, what's the perfect percentage proportion of wind and solar? Excellent question. I seek the answer. I don't know, but probably in Texas. So at least in the nation, right? The nation right now is producing 38% of its electricity from combined cycle gas. And 30 years from now, it's going to be producing 39%. And it's going to be backfilled by renewables to backfill retired coal. And the coal's retiring quickly. So we need to do this relatively soon because the wind and solar is going to be plugged into the grid quickly. And every time a cloud goes overhead, it reduces the electricity production. And so grid stability then becomes vital. And I don't think anybody here, I mean, we could talk about how great solar is, but I don't think anybody here wants to go through what happened in February. And that to me is I think Uri was the second most expensive natural disaster in US history, right? So, and that was just a cold snap. So we don't want to have that. And our infrastructure systems are so tightly coupled that when the power goes out, that means that the water systems go down too. And that means that the food supply is affected. So this is a really important thing to be thinking about. Anyway, my soapbox is down and I put it away. And are there any other questions? Come on, guys. It's the first in-person talk in 18 months. Rich. We relied on Dave Chapman and Tristan to try to come up. Oh, sorry. Yeah, how did we pick the five minerals? And part of that is because this is in the press, right? Everybody's talking about lithium. Lithium, cobalt. They think about the Congo and they think about cobalt. And so some of that was because they're known critical materials. The federal government is thinking about these. And part of it was, that these seem to be very, very important in these energy systems. We obviously need to broaden that. We have, Ata as a mining engineer who really understands this, and Tristan who's also studying this. So we're sort of trying to get the training wheels off with these materials, and then we can broaden that study out. And of course, many of these are co-produced, right? So you go into a refinery, and we've already been talking with cobalt companies, and they say, how are you going to do an attribution where if our refinery produces nickel and cobalt, well, how do you say this is the footprint of the cobalt and this is the footprint of the nickel? And that's tricky, and we're thinking about that. So if we start adding more and more materials, the attribution is going to be even more difficult. Other questions? I don't see any. Do I give everybody back 4 minutes?
Yeah, I think you got everybody. So everybody, let's thank Michael again for giving the first in-person talk and being our hybrid guinea pig. Great talk, Michael. I really enjoyed it a lot. Yeah. And y'all, if you want to come back again next week, next Friday at 9 a.m., we have Jerry Jensen presenting his work on a case study in integrating permeability and geological assessments. And thanks very much for coming.
Thanks everybody for being here.
Yes,
Appreciate
thank
it.
you.